What up, mathletes? Whoop whoop! All right, we are going to talk about linear and nonlinear functions. That's really one of the big things of today. And so, looking at linear and nonlinear, I want you in your notes to go ahead and just split it down the middle. By the way, the learning target for today is I will review linear and nonlinear functions. So you make sure you have that written down. And split your notes down the middle, linear on the left, nonlinear on the right. Linear is, it can be written in the form of f of x equals mx plus b or y equals mx plus b. That's called slope-intercept form. Why is it called that? It's because m, get my writing tool, m is slope, right? It's that rate of change. And what is our b? Our b is our y-intercept, okay? And f of x, don't let that fool you. F of x is the same thing as y. But you'll notice when we have multiple functions, sometimes we say h of x, or g of x, or t of x, or whatever. All it means is a function of x, which again is what y is, okay? So just keep that in mind as you're going down here. Now, nonlinear functions cannot be written like y equals mx plus b. So if you can't write it in that form, it's not linear, okay? So going down here, I'm just going to do show all, because I want you to see them. So some examples are this: f of x equals 3x minus 5. Again, mx plus b, right? It's got that form. 2x plus 1/2, or 2/3 x plus 1/2. Negative 3.2x plus 6.25. This one right here, all I got to do is I can add 2y over. I'm going to subtract 3x over. And I end up with 2y equals negative 3x plus 9. And I can divide both sides by 2, right? That's going to divide by 2. That's going to divide by 2. And we get that y equals negative 3/2 x plus 9/2. Again, mx plus b. It's a straight line. But also the big thing to notice is x is always to the 1 power and not multiplied times another variable. That's really the big trick. Over here we notice x multiplied times y. Even though x is the 1 power, it's multiplied times another variable, isn't linear. Over here we have the square root of x, which you may or may not know, that's really x to the 1/2 power, not to the 1 power. We have x to the 3rd power, x to the 2nd power. Those are not linear functions, okay? All right, moving on down. I want to talk about the different types of graphs that are linear versus nonlinear. Notice this graph right here. Boom. I could draw a straight line through it, and it would connect to every point. Because of that, this is linear, but because they're just independent points and not connected by a line, this is called discrete. Discrete is a situation like maybe a function representing buying books at a store. You don't just rip a book in half, walk up, I just want half a book. They're going to charge you for the whole book, right, whether you ripped it in half or not. You can't buy the in-between. You can't have 1.2 books. You have either 1 book, 2 books, 3 books, right? Maybe different sizes, but they're still full books. On the other hand, if we're talking about money, money doesn't include just whole dollar amounts. It includes quarters, nickel, the in-between values, right? And so because of that, that would be like a continuous function where the dots in between matter. Maybe we're talking about the measurement of something. Well, measurement includes every number in between. So because of that, that would be connected and continuous. Now, notice these dots. They're discrete, but they're not linear. They would form a parabola, kind of a U shape. This one is like a sideways half of a U. It's continuous because it includes all the in-between values, but it's not linear. So those are the difference between linear and non-linear. Excuse me. We're going to boot, scoot, boogie through some of this. We're going to identify linear functions. Remember, is it in the form of y equals mx plus b, or is it just x to the 1 power not multiplied times another variable? Let's look at g of x equals 2 of x, or 2/5 times x, right? Or 2x over 5. It's kind of a y equals mx plus b. I'm saying that's linear. H of x equals 5. That's linear. It's just going to make a line. It's going to be a horizontal line of 5, but it's still a line. Uh-oh, we have x times y. That's x times another variable. That's nonlinear. X to a power other than 1, nonlinear. Again, Now notice, this one, we could rearrange it to be the negative square root of 3 times x. X is not under the radical. So that's just x to the 1 power, and it's not times any other variable. Boom. And this one right here, again, I could subtract my 3x over and divide everything by 5. It'd be in the mx plus b form. But if you look at it, it's x to the 1 power. It's not multiplied times another variable. It is indeed linear. Let's check our answers. Yeah. Awesome. Feel free to pause this, write those examples where they go. It will help. Again, pause at any time. I kind of move through this because I'm assuming if you need to pause it for notes, you can. That's the beauty of video. But I'm not just going to sit here and wait for dead air because that is irritating when you don't want to pause. So select all the graphs that represent a linear function. Okay, can we connect these points by a straight line? Yep, it's linear. B, well, it looks like 3 straight lines, but not one line could cover any of this, so it's not linear. Clearly a curve, not linear. This is a line, linear. See how that works? Now looking at tables. If we want to find out if something's linear, we check the growth of it, right? So for example, I'm looking between, I know there's a whole story problem, I'm not worried about that right now. I want to look at what's the growth happening here. So if I look the growth in between 0 and 1, so the time he cycled in hours. So between 0 and 1 hours, he has distance remaining of 150 to 128, so he cycled 22 miles, right? Is that 22? Yeah, that's 22. So it's going down 22 each time. What's this going down? Again, minus 22. Notice that what we're growing by, and even though it's growing negatively, it's still a growth, is the same each time. It's 22 each time. Because of this, we know that it is a linear function if the growth is the same. If the growth was changing, that would be nonlinear. But it's the same, so it's linear. The distance remaining in the bicycle trip is modeled by a linear function. It's linear. Now I want to talk about intercepts. We're kind of overviewing like 4 years of math in like 15 minutes, so it's good times. All right, we're going to talk about x and y intercepts, okay? X-intercepts are where it crosses the x-axis. A couple things you're going to notice. Anywhere along the x-axis, the value of y is 0. That's why an x-intercept is always going to be in the form of a coordinate, right? And y is always going to be 0. I always say it's my butt cheek with the dimple, or it's my butt with the dimple on the right cheek. Kind of looks like that, doesn't it? And then this will just be whatever the value of x is at that point it crosses. It's the point it crosses the x-axis. Right here in this case, it was -2. The y-intercept, however, is just the opposite. It's where it crosses the y-axis. And all along the y-axis, guess what? The value of x is 0. So we're going to put the dimple on the left cheek. And then it's going to be whatever the value of y is there. In this case, the x-intercept is or the y-intercept is at 3. All right? Again, pause the stuff. I'm going to erase it. I don't think there's anything more on this page. So we're going to look at x and y intercepts. We're kind of just skipping through a lot of different math here. If I look right here, I see an x-intercept along the x-axis at 1, 2, 3. So that's x equals 3. And then the y-axis, 1, 2, 3, 4. So that's down -4, right? Boom. There we go. And we can have them of nonlinear functions. So if I'm looking at this right here, where's my y-intercept? Well, it's right here at 1. So we're going to look for a y-intercept of 1. It's one of these two. And then let's look at the x-intercept. It seems to cross right here. See how it kind of goes down close, 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 but right here at x equals 3. So 1, x equals 3, that's B. Yeah. And what do intercepts mean at times? Well, let's look at that. Let's look at them from a table. So the junior class is selling raffle tickets to raise money for the prom. The table shows the number of tickets remaining to be sold at the end of each week. Okay, so let's look at our x-intercepts. What are the intercepts? First of all, remember, get my writing tools, the x-intercept is where y equals 0, right? And the y-intercept is where x equals 0. So because of that, I'm going to look right here. Everybody knows this is like my x, this is my y, it's just how it works out. X is usually an increment of time. And at x equals 0 is week 0, and there are what? There are 500 tickets to sell. At x equals 5 weeks, y equals 0, so that means after 5 weeks, there are 0 tickets to sell. So let's write those down. The x-intercept is at 5 weeks, right? It's at that where y is 0, and the y-intercept is where x is 0, it's 500. Look at that. What does it want to know? Select the best interpretation of the y-intercept. Well, the y-intercept is where x equals 0, so that means at x equals 0, there are 500 tickets to sell. So, the class had to sell a total of 500 tickets. That looks good. There we go. If we were to ask about our y or our x-intercept, that's where y is 0. That would tell me after 5 weeks the class had sold all 500 tickets. That's what it would mean. Now we're going to talk about symmetry. I know we're just jumping around. So there's two types of symmetry. There's line symmetry that looks like this, where I can draw a line down the middle of a graph and it folds over on itself. That's that A to A prime, right? The distance between the two is identical. That happens in like a parabola type situation. Then there's a different type of symmetry called point symmetry. That's where we can rotate something 180 degrees and it lines up on itself. So if I use this point right here and I rotate 180 degrees, see how this graph falls over on itself? And then I can draw that line, and that line goes from A to A prime is the same distance, okay? So when I draw it to the same point over here, right here, the distance between them will be the same from that point. That's called point symmetry. So let's go over to the next page and let's look at the difference between line and point symmetry. See if we can identify it. All right, there's going to be point symmetry, line symmetry, or no symmetry. Looking at A, is there anything I can do, any point I can rotate, any line I can draw that would cut this in half? I say no. Whoa, don't right click. How about this one right here? Well, what if I put a point right here? Couldn't I rotate this 180 degrees and all of a sudden it would be down there? Absolutely. That's point symmetry. What about down here? I could draw a line straight down the middle, therefore that is line symmetry. How am I going to get that? Oh no. Oh, there we go. Line symmetry. And then right here, yeah, I think I could put a point right about here, and I could rotate it, and that would rotate around and be point symmetry. Let's see how we did. Oh, gotta get it to stay there. Look at that. It all turned out right. So there we can see the difference between line and point symmetry. I know we're rushing through this pretty fast because a lot of you can pause, but a lot of it is just saying, oh, this is what it is. Now I want to talk to you about even and odd functions, and I'm going to ignore all that nonsense right there. What I really want you to know is this. Even and odd functions, it comes down to this. Graph it. Once you graph it, let's get our nice little XY axis right here. There's all sorts of proofs we can do, but I'm not too worried about it. If you graph a line, and once you graph it, the two ends are pointed in the same direction, then that is even. And it doesn't matter what the line does. So let me do a different line. What if the line went, I don't care how much it's moving around, juking and jiving, as long as the left and the right side are pointed in the same direction, it's even. In the same way, if, here, let me I'll draw it right here. Sorry, it's going to be kind of in the middle of everything. The opposite of that is an odd function. If at the end of the function they're pointed in opposite directions, then it is odd. So this one, the left side's pointed down, the right side's pointed up. That's an odd function. And again, it doesn't matter how weird it gets in between. See how weird that got? But guess what? It is an odd function. So there we go. That is the difference between even and odd functions. Let's go ahead. We're going to go to the next page. Let's take a look at it. You will notice that, are these both pointed in the same direction? Yes, they are. So what is this? This is an even function because both ends point in the same direction. And does it have any type of symmetry? Yeah, I could draw a line right down the middle that has, we're going to call it y-axis symmetry because the line we're going to draw is y-axis, is the y-axis. Right here, that line. Okay? So let's check it, see if we did good. Boom! And now we're there. All right, with that said, peace out.